Welcome back to Reconstructing Gravity. This is Ted Cole again on chapter G7 called dFlowrate dt. And if that sounds a little bit like calculus, it is. We're just going to do a little bit of calculus towards the end of this video, but nothing too difficult. And we're going at some of our space flow issues with several important ideas. We're going to be pulling together some threads of thought, things that have been brought up in previous videos. We're going to go at them now and dig into this flow issue a little bit more. Now, as you know, if you've been following along, we've got multiple puzzles having to do with space flow, but sometimes having multiple puzzles is better than having just one puzzle. The different problems can sometimes help solve each other. Stick with me and you'll see what I mean. First, though, remember, we've had great success so far by using this flow model. We got a good answer for gravitational time dilation directly related to our special relativity constructive model. And the same flow model worked to explain physically why masses drop at acceleration g, also directly related to the constructive model. So it's going good. We just got to work on this flow problem. Remember, both of these successful models of gravity worked by postulating that the light-bearing medium of space moves towards a planetary mass following the escape velocity function for that planet. Buckminster Fuller said, "Thinking is a momentary dismissal of irrelevancies." So let's just consider an isolated Earth and how gravity works for it. We're going to ignore atmosphere. We're going to ignore any other planets as the sun and everything else. We're just going to have a planet out there. We're going to have masses falling towards it. We're going to look at the space around it and consider that. It's the simplest possible way to approach it. So let's dig into this flow problem a little more. We said that the flow, the speed of space towards Earth that would make our gravity model work is the escape velocity, which is the same as the speed a mass has as it falls to Earth from an infinite distance. And as you go up from the surface of the Earth, that speed of escape velocity drops off, but relatively slowly, compared to the speed you would have if you had a normal flow, like something like water through a pipe, because that in a tapered pipe like that, the area is proportional to 1 over the radius squared. So as you go up from Earth on that basis, the speed would drop off much more quickly. So what we said before was, in order to make our flow model work, we have to have some loss of flow as we come in towards the Earth. And so what we're going to do is we're going to look at this flow of water. We're going to look at this pipe and see what that would mean in terms of how can you drop your flow rate and how does that affect the velocity. So here's our water pipe model. It's a tapered pipe. We're just showing 2 dimensions, but this is the constant flow rate. The velocity, which is the red arrow, you can see is very large at the left, but drops off very quickly as you go to higher distances, as you go to the right, which is shown on the graph at the top as the bottom curve. Blue, which is the flow rate, is constant all the way through. That's a normal flowing condition for, say, water in a pipe, tapered pipe. But suppose for a moment that we introduce a leak. We let some of the water flow out the side of the pipe instead of getting to the end. Well, everything upstream of that leak, the flow will be increased. You have to increase the flow to get to that leak as well as to get to the end of the pipe. And this will increase the velocity upstream of the leak also. How about multiple leaks, multiple large leaks? Now we're starting to actually increase that velocity back up the pipe. All right, let's just increase these leaks until we get that velocity curve up to the upper curve. Let's see what this looks like. Wow, it takes a lot of huge leaks, right? Look at how much the flow rate has increased. in order to get the velocity to be up to the higher curve, to the escape velocity curve. Mental note, save this fact for later. We'll come back to it for sure. What did we learn from that? Didn't seem to answer a lot of questions, but what we learned is in order to have space move towards Earth at the escape velocity, meters per second, there would somehow need to be a huge decrease in flow rate, cubic meters per second. How can that possibly happen? Now let's switch gears and try a different thought experiment. Remember, again, escape velocity is the speed a mass would have if it fell to Earth from an infinite distance. And if you could put rings on it and watch it fall in, it would look something like this. That black circle in the middle is Earth. And these are rings of space falling to Earth at the escape velocity. Back in video G2, when I was talking about the G rocket, I said that balls fall differently in an accelerating rocket than they do on a gravitational field like around Earth. Balls don't drop in parallel lines, they drop radially towards the center of the Earth. And also, importantly, if balls are dropped at the same time from different heights, the lower ball will always have a higher speed than the upper ball, and their distance between them will increase because the lower ball, well, as you saw from our picture we just had, the distances increase between the rings as you go down. In Newton's terms, that is basically saying that a ball that's closer to Earth has a larger force accelerating it, so it will accelerate a little bit faster than a higher ball. And the lower ball will always be lower than the higher ball, so the lower ball will always be accelerating a little bit more, tiny bit more than the upper ball. So let's put these facts together. Einstein used these same facts, of course, in a different way because he had thrown space out of the picture altogether. He was just working in mathematical space-time, so completely different thing happened there. But let's put it together an experiment that uses these facts. Imagine that we're in a spaceship that is in free fall, and it's falling exactly at the escape velocity of Earth. And we set up an experiment. We place 8 small balls exactly at the corners of a cube. Remember, we're all weightless in free fall, so the balls will all just float exactly where we put them. Now, granted, this would be very difficult to do, but we have a special machine that can release them perfectly without giving them any force. So they're not going to move in any direction. They're just going to sit perfectly in this cube in the middle of our spaceship as we free fall. Now, here's the important point. If we are, in fact, dropping with space, not through it, if we're dropping at this escape velocity the same as space is, then the space inside the cube would remain inside the cube. No space would pass through an imaginary wall of the cube. Space inside would stay inside, the space outside the cube would stay outside. What would we see? Well, those effects that were mentioned previously. The balls would move together closer in a sideways direction, but farther apart in a vertical direction, like this. The important question is, would the volume of space inside the balls be constant? We could always measure the height, distance, and the width between the balls and compute the volume of that space. No, that space inside that cube would be getting smaller and smaller as the shape changed. It's a decreasing volume. In fact, the rate of volume change of that cube is the same as the rate of volume change of these shells of space as they all fall in towards Earth. And I computed the volume of the shell over equal time intervals as they fell into Earth, and they lose an equal amount of volume in equal amounts of time. And I showed that plotted down on the graph at the bottom and with the numbers over at the right. Well, I threatened to introduce calculus at some point, and that time is now. So those familiar with it can stop and study this page if you want. Basically, what I'm doing here is from the definitions of flow rate as area times velocity, and using the chain rule, I'm computing dFlowrate dt, rate of change of flow rate with time, with the chain rule, dFlowrate dr times dr dt equals dFlowrate dt, where dr dt is the velocity. So it turns out, very interestingly, that this dFlowrate dt is essentially a constant, 12 pi times g, big G, Newton's big G, times m, the mass of the planet. The r washes out of the equation, and so it becomes a constant that depends only on the mass of the planet. It's a very interesting fact. So study it if you want. Otherwise, just remember that this change in flow rate has been found to be a constant that depends only on the mass of the planet. And for Earth, 12 pi gm is 1.5026 times 10 to the 16th cubic meters per second. And that's exactly what we saw. The table I did earlier from that cube drop experiment, if we divide by time twice, that's a change in volume per time, that's exactly what 12 pi gm is. So it matches the experiment we had. You probably also remember a few videos back I was questioning what the units of G meant. And sure enough, flow rate units are cubic meters per second. And so the units of G can be read as dFlowrate dt per kilogram. That's exactly consistent with this equation we're finding here. That's a constant. So maybe there is some meaning to G after all. If this space moves at escape velocity postulate is true, at least we've discovered a relevant fact about it. dFlowrate dt equals 12 pi gm. There's going to be more coming, more things to discover, but this is a step forward. Thanks for watching. Please like and subscribe. Remember, you can find full outro tracks on my YouTube homepage playlist tab. Catch you next time.